Good morning everyone. My name is Saket Gaur Edigi and today I will presenting my research project titled Real-Time Anomaly Detection in Urban CCTV using Deep Autoencoders. This research was conducted under the supervision of Dr. Christian Horn, whom I thank for continuous support, guidance and feedback throughout the project. This presentation is about designing and comparing various machine learning and deep learning models to detect anomalies in city CCTV systems. The aim is to find which models can reliably detect unusual events in real time, making urban surveillance smarter and more efficient. Now we will go to the introduction part. Smart cities across the world rely heavily on CCTV systems for public safety, traffic monitoring, crime prevention, and emergency response. However, these CCTV networks generate massive real-time video streams that are impossible for humans to monitor entirely. Traditional vision techniques such as motion thresholds, background subtraction, rule-based logic are not capable of handling modern urban environments. These methods fail when scenes are crowded, illumination changes, objects overlap, or camera angles differ. So there is a clear need for automated systems that can understand both spatial information, what objects look like, and temporal information, how objects move over time. My study compares different machine learning and deep learning models and evaluates which of them is best suited for real-time anomaly detection. And problem and need. The problem is straightforward but extremely challenging. Urban CCTV systems generate far more data than human operators can process. Even with a highly trained team, individuals can only watch a few screens at once, and human fatigue leads to missed incidents. Classical anomaly detection algorithms have limitations because they depend on predefined rules and handcrafted features. In real world CCTV, the environment is highly dynamic. Pedestrians walk in unpredictable patterns. Vehicles may enter pedestrian spaces, lighting changes from day to night, and weather affects visibility. Real-time systems require high accuracy, low false alarms, and extremely low latency. This makes the need for automated, intelligent, and reliable anomaly detection systems extremely important. Cities need systems that can assist human operators, reduce workload, and improve response speed. Next, we will go to the motivation. My motivation comes from seeing the rapid adoption of AI in smart city surveillance. Today's cities deploy thousands of CCTV cameras. These cameras continuously produce video streams that contain important behavioral patterns. What attracted me to this problem is that anomalies are rare events, which means we often don't have labeled examples. This makes supervised learning difficult. However, autoencoders are powerful because they learn only from normal behavior. We don't need labeled anomalies. The model itself learns this is what normal behavior looks like. Anything different is suspicious. My research aims to bridge the gap between prototype research and practical smart city deployment, keeping both accuracy and real-time constraints in mind. Ultimately, I wanted to understand which model truly works best is in real-time CCTV environments. And the dataset I used the UCST PED2 dataset for experiments. This dataset has been widely used in academic research for video anomaly detection because it has a clean structure and good annotation. Key features include a fixed overhead camera capturing pedestrian walkways, short video clips of around 200 frames each. Training clips contain only normal pedestrian motion. Testing clips include anomalies such as bicycles, skateboards, cars, and vehicles entering pedestrian spaces. The dataset has a static background and controlled geometry, making it easier to focus on model behavior rather than dataset complexity. Although it is a controlled dataset, it is extremely useful for benchmarking because nearly every research paper uses it, allowing direct comparison. And the project goals. The project has several goals. Construct and compare different categories of anomaly detection models. Classical machine learning model, autoencoder models, prediction based models, and generative based models. Designing a spatiotemporal autoencoder that captures both appearance and motion. This was an important part of my contribution. evaluating the performance using multiple matrices like AUC score, precision, recall, FN score, and also consider throughput FPS for real-time feasibility. Build a unified pipeline so that all models share the same pre-processing, data splits, and evaluation logic. This allowed a fair comparison. Next, we will go with the literature review. The literature review shows a clear evaluation in video anomaly detection techniques. Early systems relied on handcrafted features and classical machine learning models, but these break down in dense or complex urban environments. Autoencoders became popular because they model reconstruction error, but pure spatial autoencoders miss the temporal dynamics of motion. Recently, 3D CNNs, convolutional neural networks, and convolutional LSTM models, GAN-based models, and memory-based models have shown strong performance. However, a big gap is that many studies completely ignore real-time processed speed, hardware limitations, privacy requirements, and deployment scalability. These gaps demonstrate why a comparative and practical evaluation like what I performed is necessary. Autoencoders are used to reconstruct regular frames and find anomalies by reconstruction error. We can see here the isolation for forest ROC curve and KNN for ROC curve. There is a huge difference between these both graphs. My research is driven by the following gaps: lack of real time performance reporting. Most studies focus only on accuracy, ignoring latency and FPS. Very limited deployment focused research. Issues like edge processing, multi camera scaling, and computational cost are underexplored. Insufficient hybrid models. Many models either focus on spatial features or temporal features, but not both. Dataset limitations. Benchmarks like UCSD are small and clean. Real world CCTV is much more chaotic. Domain shift challenges. Models often fail when the camera angle or environment changes. These gaps justify the need for research I conducted. Ethical concerns. Ethical considerations are critical when dealing with surveillance systems. CCTV monitoring naturally raises concerns about privacy and data protection. AI models must be used responsibly, transparently, and within legal boundaries. In my study, I only analyzed that behavioral patterns, not identities. The models are designed to assist human operators, not autonomously enforce decisions. All processing was done on publicly available anonymized datasets. Real deployment must comply with the European AI Act and India's DPDP Act, which require transparency, data minimization, and secure storage. Ethics is not an afterthought, it is an essential design principle for AI in surveillance. And in the model implementation, why I chose these models. I selected these models from more four major families to understand their strengths and weakness. There are classical models, autoencoder models, predictive models, and generative models. In classical models, I chose one class SVM, isolation forest, KNN, and local outlier factor. These act as baselines to show the limitations of traditional machine learning models. In autoencoder models, I choose autoencoder models like to learn to reconstruct normal frames. Anomalies cause high reconstruction error. Predictive models, convolutional LSTM autoencoder and predictive CNN learn to predict future frames. Anomalies cause large prediction errors. Generative models, GAN-based models generate realistic frames of normal behavior. Anomalies appear when reconstruction diverges. This selection allows a complete performance comparison. Spatiotemporal autoencoder. The spatiotemporal autoencoder is designed to capture both spatial appearance and temporal motion patterns. It uses 3D convolutions or convolution LSTM layers to analyze results Hybrid and prediction-based generative models were based in UCSD PDDU dataset. Autoencoders gave good reconstruction but had issues with unique anomalies. False positives were maximized maximum in classical models. And conclusion and future work. Simple and classical AEs are less efficient than temporal and hybrid architectures. Anomaly detection must be done with the help of spatial temporal modeling and in the future work, multi-city, multi-environment evaluation, diffusion models, and test transfer based anomaly prediction. Thank you. Thank I will explain the code for project title, the real-time anomaly detection in urban CCTV using autoencoders. I'll share my screen. Here, the first two lines downloads the UCSG dataset and extract the dataset so that the video file becomes accessible. And the pip install pyod function it installs the pyod, a specialized library for outlier and anomaly detection. And now we are importing the libraries. These are the code begins by importing essential libraries required for building an anomaly detection pipeline using both machine learning and deep learning approaches. The OS module is included to handle directory navigation and file system operation, which is important when working with datasets stored in folders. The CV2 library, part of OpenCV, is imported to load and process images, perform resizing, grayscale, conversion, and other computer vision tasks essential for preparing frames for model training. NumPy is included as NP to create manipulate arrays as image datasets and model inputs are primarily handled in numeric matrix form. And the base path USCD anomaly dataset. And the code defines three configuration variables that control how the USCD PD2 anomaly detection dataset will be processed. The first line assigns base path to the directed path USCD anomaly dataset, which tells the program where the dataset is stored. This is necessary because the UCSD PD2 dataset includes videos of pedestrian walkways typically used for anomaly detection research, and the models later in the script need a reference point to load training and testing frames. And now here we are extracting the futures function is designed to convert each video frame into a compact numerical representation that can be used by anomaly detection models. The function begins by resizing the input frame using OpenCVs, ensuring that every image is scaled to the predefined image size, which is typically 64 and 64. And now here we are loading the loads UCSD split function is responsible for loading and pre-processing frames from UCSD PD to anomaly detection dataset. It begins by constructing the full path to either the train or test directory using Python's OS path join. Depending on the value passed through the split argument, the function then retrieves a sorted list of all video folders inside this directory, ensuring that the dataset is processed in a consistent and reproducible order. That the load ground truth function is designed to load the frame level anomaly labels from the UCSD PD2 dataset, which provides ground truth mask in separate folders. It begins by defining the path to a test directory where both test videos and their corresponding ground truth folders are stored. And then use of HOG. This code block configures the future extraction process to avoid using histogram of oriented gradients futures and instead rely on raw pixel values. By setting USC HOG for equals to false, the extract futures function will skip HOG computation and simply flatten each image after resizing it into their defined image size. Printing training KNN anomaly detector. This code begins by printing a message to indicate the KNN based anomaly detection model is being trained. The model being used comes from the PYOD library, which provides specialized algorithms for outlier detection. The evaluation process. For the KNN anomaly detector begins with generating predictions on the test dataset using vibrate equals to knn.predict x test, which output labels in the form of 1 for normal and -1 for anomalous samples. We got ROSICO and Precision for KNN model. Hmm. For autoencoder models device, this line of code is used to determine whether the system has access to a GPU, and if so, instruct PyTorch to run all tensor operations on it for faster computations. The get autoencoder function is designed to return different types of autoencoder neural network architectures based on the model type selected by the user. Autoencoders are unsupervised neural networks used to learn and compress the representations of data and detect anomalies using reconstruction error. The train autoencoder function is responsible for training different types of autoencoder models using a standard reconstruction-based learning approach. It begins by transferring the model to the appropriate computation device, preferring a GPU if available, and setting up the Adam optimizer along with the mean squared error loss, which measures how well the autoencoder reconstructions it inputs. Mm, The create spatiotemporal clips function is designed to transform a sequence of image frames into spatiotemporal clips that can be used as input for 3D convolutional autoencoders. The run autoencoder pipeline function integrates the full workflow for training and evaluating different types of autoencoders, convolutional, stacked, or spatiotemporal on anomaly detection tasks. It begins by printing the chosen model type and initializing the appropriate autoencoder architecture using get autoencoder function. When the command run autoencoder, mm, the function is used executed, it launches a full anomaly detection workflow using a convolutional autoencoder. Here, the create sequence function is designed to convert individual image frames and their corresponding ground truth labels into fixed length temporal sequences, which are required for models that learn spatio-temporal dependencies such as LSTM based or convolutional temporals. And here this line prepares the UCSD to test dataset for temporal sequence modeling before calling the sequence generation function. The test images are reshaped from flattened vectors back into their original 64 into 64 spatial form using reshaping, ensuring that each frame is correctly restored as a 2D frame. And the convolutional autoencoder function implements a simplified spatiotemporal anomaly detection pipeline using a 3D convolutional autoencoder architecture. Its purpose is to learn temporal reconstruction patterns from sequences of video frames and then use reconstruction error on the last frame of each sequence to identify anomalies. This line triggers the complete convolutional LSTM style 3D autoencoder anomaly detection pipeline using the previously defined function. The first argument X train shape -16464 takes the raw training images that were loaded without HOG features and reshape them back into their spatial form of 64 into 64. This code segment is evaluating the performance of convolutional LSTM autoencoder used for anomaly detection. After training the model, the reconstruction errors from the convolutional LSTM autoencoder are stored in the variable convolutional errors. These errors indicate how well the model is able to reconstruct each input sample, with higher errors often corresponding to anomalous or abnormal patterns. The predictive CNN function implements a predictive convolutional neural network CNN designed to forecast the next video frame in a sequence and use the prediction error for anomaly detection. The video is that abnormal frames are harder for model to predict accurately, so they produce higher reconstruction or prediction errors. The GAN generator function defines a simply fully connected generator network for a generative adversarial network. Its purpose is to transform a low-dimensional latent vector typically sampled from a random distribution such as Gaussian noise into a high-dimensional image representation of size 64 into 64. The CAN discriminator function defines the discriminator network for a generative adversarial network designed to differentiate between real images and those generated by the generator. It takes an image of 64 into 64 as input. The first liner layer reduces this high dimensional input to 512 units, beginning the process of extracting features that help identify authenticity. The train function implements the full adversarial training pipeline for a basic GAN. It begins by converting the flat-end training images into PyTorch tensor and loading them into a data loader, which enables efficient mini-batch training. The generator and discriminator are then instantiated using the previously defined architectures and move to the appropriate computation device such as a GPU if available. Both networks are optimized using the Adam optimizer, and binary cross entropy loss is selected as the objective function, which is standard for binary real versus fake classification of GANs. The, the GAN anomaly score function evaluates anomalies by leveraging the generator's ability to reconstruct normal data patterns, unlike typical autoencoders that directly encode and decode input images. This method uses latent space optimization to identify how well a GAN generator can reproduce each test sample. The GAN autoencoder function defines a hybrid architecture that combines a traditional autoencoder with a GAN inspired generator, providing a more flexible foundation for anomaly detection. The function begins by creating a generator network using the previously defined GAN generator, which maps a latent noise vector into a reconstructed 64 into 64 image representation. The train GAN autoencoder function implements a dual training strategy that combines a GAN generator and a standalone autoencoder to create a hybrid anomaly detection framework. The process begins by converting the training dataset into PyTorch tensor and loading into data loader for mini batch processing. The GAN autoencoder anomaly score function generates anomaly scores using a hybrid combination of GAN generator and trained autoencoder designed to measure how well a test frame fits the distribution of normal data. And here we got the ROC curve for GAN autoencoder and a precision recall curve for the GAN autoencoder. This precision recall curve shows the how GAN autoencoder's anomaly detection performance changes as the decision threshold is varied, and a precision on the y-axis represents the proportion of predicted anomalies that are actually correct, which recall on the axis represents how many true anomalies the model successfully detects. Thank you.